We are discussing now about orientation polarization. Another name for orientation is dipolar or molecular polarization. So the examples for this orientation polarization is H2, N2, O2, Cl2. This does not carry any dipoles because the center of positive charge and center of negative charge will get coincides. So the molecules like CH3Cl, H2O, HCl carries dipoles even in the absence of the electric field. So this indicates that certain materials have permanent dipole moment and certain materials do not have the permanent dipole moment. The net dipole moment is negligibly small since the molecular dipoles are oriented randomly when there is no applied electric field. In the presence of electric field, all dipoles orient themselves in the direction of the field as a result of net dipole momentum. So this is the relation for orientation polarization. PO, orientation polarization for n molecules, that is n mu. Here the dipole momentum is for the molecules. It is represented by n square mu square E by 3 kT. K is the Boltzmann constant and T is the absolute temperature. By substituting the relation, we get n alpha naught E. Here mu is the dipole momentum for the molecules. So orientation polarizability is represented by mu square by 3 kT. Here T indicates that orientation polarizability depends on temperature. Previous polarizations does not depend upon the temperature. Total polarizability is the combination of electronic polarizability, ionic polarizability and orientation polarizability. So the combined relation is called Langevin-Debye equation. Already we derived electronic polarizability as 4 pi epsilon naught r cube. So this polarization depends upon atom radius. Later ionic polarizability, that is E square by omega naught square 1 by capital M plus 1 by small m. Here m is the masses of the ions and this is also independent of temperature. So last polarizability which we study is orientation polarizability. The relation is mu square by 3 kT. Among all these relations, electronic and ionic polarizability are independent of temperature, but orientation polarizability depends upon the temperature. So this is the total polarizability relation. This is also called as the Langevin-Debye equation.